Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck as we continue our journey through mathematics. Today, we're going to explore what we call conic sections, and hopefully by now you've seen the video introduction that I have listed right here. This video introduction really kind of goes through the details and the terminology of what we're talking about through our chapter 10. What happens, in case you haven't seen it, I encourage you to stop and actually watch it. But what happens is we are going to take one line, take a second line, and then with that second line, we're going to revolve the second line around the first line. And in doing so, we create what we call the double napped cone. Now, the reason why we call these conic sections is because we'll then take a plane and we'll cut we'll cut this cone with the plane and form all of the different what we call conic sections. You guys should be familiar with this one. This is the circle. The circle is what we began our school year with. Then we also did parabolas, which is 10.2. And this is what our focus is going to be on today. And the parabola is created when you have this generating line with the exact same slope. It's really gradient when you talk about it in a three-dimensional format, but with the same gradient cutting through the cone, you create what's called the parabola. In 10.3, we are going to discuss ellipses and what happens with an ellipse. And by the way, a circle is a special form of an ellipse, is what happens when you cut it at a slight angle. And then we're going to go into 10.4, we're going to discuss the hyperbola. Now, all of these have extreme real-life applications. In fact, conic sections are some of the oldest form of mathematics. When you start talking about astronomy, conic sections are very, very involved in astronomy. You're talking about anything involving forces, specifically gravitational forces. That's where you're going to see a lot of the work with parabolas. But also, as you start looking at it in more of a three-dimensional idea in terms of the planetary systems, you'll see that a lot of the events that happen in the solar system do involve conic sections as well, because there's a lot of rotation. And then sound waves, light waves, all of the, I know this doesn't, the conic sections, a lot of people are going, you know, where are we going to need this cone and why? Well, these conic sections are really kind of like a connection, a visual way of showing what happens with light and sound in the three-dimensional world. So with all of that, I encourage you to look at the second video, and hopefully you guys have already watched that, which talks about the real-life applications. The parabola starts roughly about at 9:30, although it's kind of teased at the very beginning with the introduction to that whole video. So without further ado, for the sake of this video, I want to take a look at and say, what is a parabola? The parabola is really the collection of all points P that are the same distance from a fixed point and a fixed line. So this fixed line, as we can see represented here, is what we call the directrix. The fixed point is what I have right here. Now with that fixed point, if that fixed point gets moved up here, then this distance will be the exact same as this distance. The vertex is actually the shortest distance, so whatever that distance is, that distance as well is going to be the same. And again, geometry kicks in that what ends up happening is you're creating similar triangles, or really equal triangles. So let me go ahead and erase the little drawings that I did on here so that we could talk about all these different parts. Now, the axis of symmetry is going to be that generating line. We have our vertex, which we said was our shortest distance. So our shortest distance is what we're going to call A right here. So this distance A and this distance A should be the same. And as we go into our exploration, what we're going to focus on is that distance A represents the distance from vertex to focus. So some vertex to focus, that distance is A. And then also vertex to directrix, that distance is A as well. So to create this point, what you've seen that I've done up here is, I'm trying to match up the right color. We have our vertex, which we have at 0, 0. We have our focus, which is going to be at the coordinate A0. That focus is, I'm going to highlight in purple here. That A comma 0 and the point x comma y, which I have right here, that's what I have highlighted over here. And so distance, we really have the distance formula. Our distance formula is simplified. I'm not going to walk you through all of those steps, but our distance formula is simplified on this side. Then we have the second point, which is the point on the directrix, which I'm highlighting in this reddish color. Actually, let's go to this color just so we can match up. That's going to be this distance represented right here. That distance is measured by x plus a, and a lot of people go, why would that be x plus a? That's x minus negative a officially, as we're looking at those 2 points. So I'm going to go ahead and highlight that so you can see it. Now, as you scroll through the mathematics on here, what ends up happening is a lot of stuff cancels, and we have this generic equation, the y squared equals 4ax. Now, this is not the form that you guys are familiar with. The form that you're familiar with is y equals x squared. What we're doing is we're manipulating this so that we can put this on either a vertical or horizontal axis based off of whether our parabola is opening horizontally and vertically. We'll go into that discussion a little bit further down. You'd like to see it as y equals ax squared, y equals a times x minus h squared plus k. What we're going to do is we're going to manipulate it so it's going to be of the form x minus h squared equals y minus k over a. Now, that doesn't seem very, very beneficial for you. And the reason why it doesn't is because you're not really familiar with it. What happens with conic sections, we end up working with conic sections in such a way that we're going to try to keep a lot of our notation consistent. We're going to try to keep a lot of the ideas consistent. So we're going to scrap this basic idea of what you're used to in favor of a more common format. So let's go ahead and erase that since we're not going to be focusing on that quite as much. So y squared equals 4ax. So if we have a horizontal parabola, like you see right here, it is of the form y squared, and y squared is not what you're normally used to. You're normally used to seeing the x squared. But if you notice, this is not a function. If this were a function, then it would be y equals x squared. This, by writing it in this orientation, this is now x as a function of y. That kind of goes away from the purpose of what we're doing. Let's actually focus on the geometric properties of the parabola. With the parabola, and why that parabola is so special is, as we said, the distance from the focus to that point is the same as from that point to the directrix. Now, where in real life application does this matter? If you take a look at light waves, if you send light waves out, they will bounce off that parabola in that general direction. So if I send the light wave out here, focuses off that direction, what you see is really what flashlights do and what the headlights do in a car. You have what's called a paraboloid of revolution, which is really just a three-dimensional parabola. And that paraboloid of revolution shoots all the light in that same direction, creating a very focused beam. Now, on the flip side, let me do this in a different color. What happens if you're actually receiving signals, they're coming in, and they hit the parabola at all the different spots? What happens is they collect into the receiver, and this is really more sound than it is light. The sound waves come into the receiver, and those sound waves then are really you get a focused audio of anything that's happening. If you take a look, or happening on the outside, if you look on the sideline of a sports event, you'll see people holding these paraboloids of revolution so they can capture the sound. If you think about satellite dishes do the exact same thing. They're not just sound waves. I mean, I guess there are sound waves, but they also transfer the video images as well. So with all of that said, that's an introduction to our parabola. We do have a very, very special characteristic of this parabola that we are going to emphasize. That characteristic is called the latus rectum. The latus rectum is actually the shortest chord going through the focus parallel to the directrix. So let me go ahead and erase all of those so I can show you the lattice rectum. The lattice rectum is going to be the shortest chord that goes through the focus that ends up being parallel to the directrix. So if you look at that, these two are parallel. As we graph our parabolas, we are going to be using what we call the lattice rectum points. So this point right here, this point right here. We're also going to use the vertex to create really the 3 points essential for making this parabola. For some of the problems, we're going to do a few more points, but those are going to be the 3 points that I care the most about. So let's get into it. What you see at the top of our screen right here is just a generalization of what's happening. What happens if you have an equation that looks like this? What orientation does that have? This is y squared equals 4ax, like I showed you above. What happens is this axis symmetry is the x-axis, and it opens right, as you can see in the picture above. If you have a negative value means that you're going to open left. And then we have these two, which are what you're more familiar with. And this is where I said you are really more familiar with it written like this. But we're going to have it in the form of x squared equals 4ay intentionally, because it really sets up a lot of the ideas of what we're doing with conic sections. So all the information that you see over here isn't quite as relevant. If you want to memorize that, feel free to memorize all those different pieces. I prefer to focus on these two sides because I want to know, based off of the equation, what is the orientation that results from it. And that's where, as you see me do my work, I'm going to really work from there. Now, this A value, if you remember, that A value is the distance from vertex to focus, or vertex to directrix. So we're going to utilize that A value as we create our graphs. Remember, there's a lot that's going on geometrically, but how we create the graphs, we're going to do it from a little bit more of an algebraic side, and then we'll try to make those connections geometrically. So our first problem, x squared equals 12y. Is this, which form are we looking at? The x squared equals 12y. If we look at the table up here, we see that that should be the axis symmetry is the y-axis opening up. Now, that's the last time I'm going to reference that, because I'm going to look at this and say, what seems to make sense for me? The fact that this is x squared means this is of the form y equals x squared that I'm familiar with. And because it's a positive value, I know that the y equals x squared, which should be one of those two, ends up only being the one that opens up due to the positive value. So this does have, like all of these problems that we're going to be working with right now, have our vertex at 0, 0. And we know that 0, 0 actually works on here, because if we do make a t-chart, and that t-chart is going to be kind of important in terms of like making everything. If the x value is 0, the y value has to be 0 as well to make this equation true. Now, this is where I'm going to break this equation down a little bit more, and I'm going to look at this equation not just as x squared equals 12y. I prefer to look at this as x squared equals 4 times 3 times y. And why do I want it in that form? Because now I have it in the x squared equals 4ay format. So x squared equals 4ay. And that x squared equals 4ay, what that tells me is my a value is 3. And I care about that a value of 3 because it's going to combine with the fact this parabola opens up to say, where this is my vertex, if I go 3 units above the vertex, this becomes my focus. And then similarly, and really that a value of 3 is what I cared about. So that a value of 3. If I go that a value of 3 in the backwards direction, we can create the directrix. So once again, kind of like how I thought through this was, I looked at this and said, based on this equation, it's x squared, so it opens up or down. The fact that x squared is a positive value means that it opens up. And then from that, I'm going to find that a value of 3 so that I can create the focus and the directrix. So the equation of that directrix is y equals negative 3. The focus point is 0, 3. The axis of symmetry, if you followed the table, you would see that the axis of symmetry is the y-axis. I prefer to give it the equation name. Let's go ahead and write y-axis. And then, what do we have left to find? I'm only really seeing 2 points in a line. What do I guess 2 lines. What do I need to find is the lattice rectum points, and I have this as L point R, just as a simplification. So the length of the lattice rectum, if you remember, the lattice rectum is parallel to the directrix. So if it's parallel to the directrix, then it's going to have the same y value as the focus, which I'm going to show right here. The y value of the focus, if that y value is 3, and this is kind of backwards on a table value, what you're familiar with. If the y value is 3, we get x squared equals 36. So that x has to be either a positive or a negative 6. So that x value is a positive or negative 6. So if I go out 1, 2, 3, 4, 5, 6, this points on the parabola, and that points on the parabola as well. So this that I have drawn in is my lattice rectum. And then what's the length of the lattice rectum? That length is 12, which, if you notice, that what's given to us in the equation is the actual lattice rectum length. And so that's why that's so important as we go ahead and generate all these values. Well, those are the 3 points that I really care about. If we really wanted to, we can make some additional points. One of the ways that we can make additional points, and I'm not going to make you do this for all of them, but I'm going to show you for this one. Can we come up with a y value that is going to give us a perfect square so we can solve this algebraically very nicely? So if you look at our perfect squares, 16, not a really good y value. We can create something. 16, 25, definitely, that's odd. We don't want that. 36 is what we used. 49, no. 64, 12 doesn't go into 64 nicely. Doesn't look like there are any y values I could use nicely. Let's go ahead and say the y value 1/3. And a lot of people are like, why 1/3? Well, if y is 1/3, then I get x squared equals 4, which means when x is plus or minus 2, the y value is going to be 1/3. We could use that to generate more points. Let's go ahead. For the sake, we don't want this video to go too long. We can create the parabola from there. Remember, let's draw that a little bit nicer. I'm only going to require the 3 points as you draw your parabola. Those 3 points are going to be the focus points, or sorry, the lattice rectum points and the vertex. So let's move on and say, how do I want you to efficiently graph these problems? So first, I want you to look at the orientation and say, because this is y squared, this is going to open either to the left or to the right. The fact this is a positive value means that's going to open to the right. So the fact that's positive means it's going to open to the right. What is my a value? If I break this up into 4 times 2 times x, that means my a value is going to be 2. And that's because this is represented in that way. Our vertex is going to be at 0, 0. So I really should put the vertex on these. So the vertex is going to be 0, 0 for all these problems. The a value matched up with opening to the right, that a value goes right here. So there's my focus. And then if I go 2 to the left, that's how I get my directrix. So my focus is going to be at 2, 0. My directrix is x equals -2. And with that said, axis symmetry is going to be the line y equals 0, which, by the way, is the x-axis. So my axis symmetry is right here. Length of the lattice rectum, going back to what I did and what we discovered on the last one, the length of the lattice rectum is 8 because that's really given to us in the equation in that way. So if I go parallel to the directrix, so I know that my lattice rectum is up and down through the focus. If I go 4 up and 4 down, the reason why 4 and 4 is I'm taking half the lattice rectum, say 4 up, 4 down. Then I can create the parabola like so. If I want anything more specific, or I want a more detailed parabola, I would definitely include some more points. For instance, if x equals 8, in this case, let's go ahead and do the t-chart. What I did was I used my last rectum points, meaning if the x value is 2, y ends up being, we have y squared is 8x. So y squared 16, so y is plus or minus 4, as you can see right there. If x is 8, then y squared will equal 64. So the y value would be plus or minus 8. We go ahead and put those points on there as well. So when x is 8, 1, 2, 4, 6, 8, 4, 5, 6, 7, 8. So my parabola was off slightly on the top. And then on the bottom, I was actually going pretty good. All right, so you can see that we can quickly create the parabolas based off of the equation, and I'm going to do that right here. So the fact that this is y squared, this y squared tells me it opens either to the left or the right. The fact that this is a negative value means it's going to open to the left, so I know my parabola is going to open like that. If I break this up into negative 4 times x, that tells me that that 4 is my a value. Let's go ahead and put all these pieces of information on the graph. There's my vertex. The fact that a is 4 means I'm going to go 4 backwards right here to create my focus. And that focus is at the coordinate negative 4, 0. My directrix is to the right 4 units. So that is going to be the line x equals 4. My axis of symmetry, once again, is going to be y equals 0. Let's draw that in. And that would be the x-axis. The length of the last rectum is not going to be negative 16 because we can't have a negative length. So the length of the last rectum is going to be a positive 16. So if we take that positive 16 and we cut it in half, that would be 8. So 2, 4, 6, 8 right here. 2, 4, 6, 8 right here. And there's our parabola created. Whoa. Nothing like getting all crazy there right at the end. So there's our parabola. Now, what happens if we're given individual pieces of this parabola? Meaning, what happens if I'm given the vertex and the directrix? How am I supposed to come up with an equation? Well, this is where it's going to be essential to understand the different pieces of this parabola. And I will start by drawing a picture. So, and this isn't going to be an extremely accurate picture. It's really just more of the visual. So if this is my vertex and my directrix is x equals 3, which is not on that side. My directrix is x equals 3. That would be over here. Then what does this tell me? First of all, this tells me that my orientation. So these two pieces together tell me my orientation. And that orientation, if the directrix is on the right side, that means the parabola is going to have to open up to the left. So that orientation tells me it's going to be a y squared, and it's going to be a negative 4ax. So that's actually how I'm going to begin. I will say y squared equals negative 4ax. And now that the fact that the directrix is 3 units away, because that's 3 units away, that tells me my a value, because once again, the distance between the vertex and the directrix is a. So I can simply plug in that information, negative 4 times 3 times x. So y squared is negative 12x. And if you notice, that's very similar to what we had in example number 3 above. Well, for problem number 5, I'm given my focus as 0, 2, and my directrix is y equals negative 2. So let's quickly graph this out. So there's my focus, and my directrix is down here. So that's y equals negative 2. Well, what does that tell me? If we know what I call the anatomy of the parabola, I know that the parabola has to wrap around that focus. So the parabola should be opening up like so. If that parabola is opening up, that tells me that I now have not y squared, but x squared equals 4ay. And so With further understanding, I know that distance is 2 and that distance is 2. With our distance being 2 there, that tells us our a value. So our a value is 2. So I have x squared as 4 times 2 times y, or x squared equals 8y. And this one, axis symmetry is the x-axis. So let me kind of sketch it out. My axis symmetry is my x-axis. The fact that it's the x-axis, the axis symmetry means that this is going to either open left or right. The vertex is 0, 0. Okay, we get that. But then it contains the point 2, negative 3. So I still don't know if it opens left or right, but if I plot that point 2, negative 3, which would be right here, that tells me we are going to be opening up to the right. So the fact that it opens up to the right means that this is going to be a y squared equals 4ax. The fact that it's y squared equals 4ax, I now can use that point, that 2, negative 3, and plug it in. That y value is negative 3. The x value is 2. And I have 9 will equal 8a. So a is 9/8. Kind of a strange value for what we're used to, but what we'll find is a lot of parabolas in the real world don't have those nice values. So y squared is going to equal 4 times 9/8 times x. So y squared will equal 4 times 9 is 36. 36 divided by 8 doesn't go evenly. Let's just go ahead and reduce that to 1 and 2. So y squared is 9/2 x. Now, what you'll find a lot of times that we do is we don't solve for a. We actually would rather solve for 4a. So if I divide both sides by 2, 9/2 will equal 8a over 2. So 9/2 will equal 4a. The reason why we want to know 4a is based off of the equation. That is our 4a value. Let's get into a couple real-world applications. Those real-world applications, we have an arch that's in the form of a parabola. Now, I know a lot of people don't think that these geometric shapes really have a lot of application, but in terms of like stresses and how like the design, I guess, the design of it in order to make sure all of our stresses are maximized, we know where the forces are going to be or going to be directed. They are in these geometric, these conic section shapes. So with that said, I'd like to go ahead and draw a picture. So we have an arch in the form of parabola with the vertexes on top. So looks like so. You calculate the focus of the arch 5 meters below the vertex. So the focus is going to be right here. I'm going to say that distance is 5. If the base of the arch is 40 meters wide, so I know that this distance right here is 40. How tall is the arch? So our goal is to figure out how tall that arch is. So now that I've kind of framed my problem, let's go ahead and assign these on an axis. So if I want to assign this on an axis, what I could do is I have one of two options. Now, really the problems that we have show that our vertex is going to be right here. And our equation, and we're going to first model this with an equation. The equation that we have is going to be x squared equals negative 4ay, because this is a parabola that opens down. Because I know the distance from the top of the arch, aka the vertex, to the focus, that tells me that my a value is 5. So this 5 right here, I can plug in and say I have x squared equals negative 4 times 5 times y. So simplifying that equation, x squared is negative 20y. Now this is where I'm going to use my other piece of information. My other piece of information is I was told that that was 40. So that means that this point right here on the ground is going to be 20 units away. And what I can do is I can I could try to say, I want to know what that y value is. That y value then tells me how tall the arch is. So if I consider this generically as the point 20 comma y, what I get is 400. That would be 20 squared. So 400 will equal negative 20y. So y ends up being negative 20. And so this distance right here, we say the y is negative 20, but that distance ends up being 20 units away. So the arch is 20 units. And what are our units? Let's go ahead and look at our problem. These are in meters. So the arch is 20 meters tall. So what we did with this problem was we took the information, we kind of sketched it out. From that sketch, we made an equation, and then from that equation, we were answering the problem based off of other piece of information. So a radio telescope has a parabolic dish with a diameter of 100 meters. So what I'm going to do, if it's a parabolic dish, I'm going to go ahead and create a parabola. Now, because we did a vertical parabola that time, I'd actually like to do a horizontal parabola. So let me go ahead and sketch this horizontal parabola. We know that this parabolic dish right here has a diameter of 100 meters. Don't like it when it does that, but okay. So this diameter is going to be 100 meters. The collected radio signals are reflected to a collection point called the focal point, which is the focus of this parabola. So our focal point, because I understand what's going on, that focus will end up being out here. How are you supposed to know? You're not. So we could generically just put our F wherever we want. So that focal point. That focal length, or the distance from the focus to the vertex, is 45 meters. So I know that that's 45. My goal is to find the depth of the dish rounded to 3 decimal places. Now, the mistake a lot of people make are thinking that the focal point is going to be along that latus rectum. That's not necessarily the case. So with that said, let's go ahead and make our equation. The fact that we drew this out in a horizontal format means that we will have y squared equals 4ax. You could have drawn this in a vertical format and had x squared equals 4ay. That would be fine as well. But I have y squared equals 4ax. That focal length will tell me that y squared will equal 4 times 45 times x. So y squared will equal 4 times 45, 4590, so that would be 180x. Then finally, let's figure out our information. So we've taken our information, we've modeled this, modeled it with an equation, and now what is it we're trying to find? Our goal is to find the depth of the dish. So the depth of the dish, let me do this in another color. So the depth of the dish would be that depth. Now, if you notice, based on how I drew this, that would be an x coordinate. We don't know the x coordinate, but we should know the y coordinate because we know the diameter is 100. So I can make this coordinate generically x comma 50. So when I fill that into the equation, I now have 50 squared is 180 times the x. So x should equal 50 squared over 180. And that would be why I have the calculator on over here. So if I take 50 squared and then divide that by 180, I get a fraction, which that's not what I want according to the directions. So 13.889. So x would be 13.889. So the depth of the dish, the depth is 13.889 meters. And if you see, going back to my picture, this is actually not drawn to scale. If this is only 13.889, that focal point should be way, way out. What ends up happening is the wider the dish, the further the focus gets away. So I will stop video 1 here so that you can pause, because this was a rather long video. And then we're going to pick up video 2 when we have our vertex away from the origin.